Azure OpenAI looks like just another API endpoint. You deploy a resource, you get an endpoint, you give it a key, you move on. This assumption, it's the liability. Here's what actually happens. You deploy Azure OpenAI without thinking about the perimeter. No private endpoints, no managed identities, no governance layer, just the model sitting there waiting to be called. And for a proof of concept, it works fine. But the moment you scale past one team, the moment you try to audit what's connected to what, the moment leadership asks for compliance evidence, everything breaks. Enterprise AI isn't about the model, it's about the perimeter. The perimeter is the structural boundary that keeps your data safe, your costs visible, and your reasoning auditable. Without it, you don't have an AI platform. You have a liability. Manual deployments create audit failures, data leaks, governance chaos. When an auditor walks into your organization and asks to see the code that deployed your LLM infrastructure, if your answer is, "We did it in the portal," you've already lost. Bicep isn't optional. It's the enforcement mechanism that makes the perimeter real. This masterclass shows you why the old model fails and how to build the hardened perimeter, the integrated structure of identity, network, governance, observability, and orchestration that transforms AI infrastructure from a security hole into a controlled, auditable, scalable platform. Why standard landing zones fail with AI. Azure landing zones were built for a specific type of workload, static resources with predictable access patterns. You deploy a web app, you know it needs network access to a database, you know which teams operate it, you know which data it touches. These patterns are stable, they don't change, so landing zones were designed around this stability. Management groups organize subscriptions by business function. Azure policy enforces configuration baselines. RBAC assigns permissions to known roles. Everything assumes that once you've deployed a resource, it stays the same. Then AI arrived. LLMs don't follow static patterns. An LLM consumes data from multiple sources: SharePoint, SQL databases, Cosmos DB, external APIs. The access patterns are unpredictable. The data flowing through the model changes constantly. The reasoning chains adapt based on input. This violates the fundamental assumption that landing zones are built on predictability. Here's what happens when you treat AI like traditional workloads. Teams deploy Azure OpenAI in the portal. No infrastructure as code, no governance layer. They connect it to a SharePoint site manually. They add a managed identity with broad permissions. It works, so they move on. Then another team does the same thing, differently. They use API keys instead of managed identities. They enable public network access. They skip the private endpoints. Configuration drift spreads across the organization. Now you have 3 ways to deploy the same resource. This is the creation of pet infrastructure, resources that can't be audited, can't be replicated, can't be secured at scale. When a third team tries to replicate the pattern, they miss something. Maybe they forget the role assignment. Maybe they enable public access by default. Maybe they skip the diagnostic logging. Each manual deployment is a copy of a copy, and with each iteration, fidelity is lost. Governance layers, Azure policy, management groups, they were designed to enforce rules about regions, SKUs, and tagging. They don't understand reasoning chains. They don't know that when an LLM accesses your knowledge base, that connection needs to stay private. They don't account for the fact that token spend is invisible until the bill arrives. The result is shadow AI. Untracked deployments, untracked token consumption, compliance violations that nobody knew existed until the audit began. And then the auditor arrives. She asks, "Show me the code that deployed this resource." Silence. She asks, "Who has access to this endpoint?" The answer is scattered across the portal, across different teams, across spreadsheets that don't match. She asks, "How is data flowing from your knowledge base to the model?" Without private endpoints defined in code, the answer reveals public internet exposure. This is what auditors find: evidence of control failure. Not because you're trying to do something wrong, but because you treated AI like traditional infrastructure when the model demands something different. That difference is what we're going to fix. The cost of manual AI deployment. The liability isn't just architectural, it's financial and legal. When you deploy manually, cost compounds in ways that traditional infrastructure never does. Not because the individual deployments are expensive, but because each one introduces a new source of divergence. Let me be specific about what happens. Your first team deploys Azure OpenAI with all the security controls, private endpoints, managed identities, diagnostic logging. The deployment works, the infrastructure is locked down, they're compliant. Your second team is under time pressure. They deploy Azure OpenAI without the private endpoints. It's faster. They know they can add them later. They deploy with an API key instead of a managed identity. Same reasoning. Faster now, secure later. Your third team uses a different pattern. They enable private endpoints for Azure OpenAI, but they forget to apply the same pattern to Azure AI Search. So now you have 3 deployments of the same architecture with 3 different security models. This is configuration drift. It happens the moment you stop deploying through code and start using the portal. Here's the problem with configuration drift in AI infrastructure. It's invisible until it costs you. Your first team's deployment is tracking token usage through application insights. Your second team's deployment sends logs to a different workspace. Your third team never enabled diagnostic logging at all. Now, when the monthly Azure bill arrives, you can't tell which team consumed which tokens. You can't attribute cost to which project used the most expensive model. You can't see where spending is accelerating. Token spend becomes a mystery until the invoice appears. By then, it's too late to optimize. You're paying for decisions you can't see. And here's where it gets worse. Managed identities that were bypassed for faster deployments. One team configured managed identities correctly. Another team used an API key stored in a key vault. A third team stored the key in environment variables. All three approaches work. None of them are the same. When an auditor arrives and asks, who has access to this LLM endpoint, you're not giving one answer, you're giving three, and they don't align. Data lineage becomes impossible to trace. In manual deployments, the connection from your SharePoint content to the LLM to the application output is scattered across different configurations, different identity models, different logging strategies. You can't draw a line from data into reasoning to data out. You can't prove that sensitive information stayed within your security boundary. You can't show which documents were used to ground a specific model response. This matters for compliance. It matters for data governance. It matters when you need to prove that you didn't expose confidential information to an external service. But the real cost comes at remediation time. If you realize 6 months in that your AI infrastructure doesn't comply with your governance policy, you need to fix it. But fixing manual deployments isn't about updating a module. It's about going back to each deployment, understanding how it was built, modifying it manually, testing it, and hoping you don't break something else in the process. I've seen organizations spend 6 months remediating manual deployments when they could have had the controls in place from the beginning. Remediation costs exponentially more than prevention, not because the fix is technically difficult, but because you're working blind. You're changing live infrastructure without knowing exactly what's connected to what. This is the hidden cost of manual deployment, not the infrastructure itself, but the cost of trying to govern it afterward. This is where Bicep changes the model. The hidden assumption. Here's where the thinking breaks down. The hidden assumption that drives manual AI deployments is this: we'll secure it after we prove the concept works. It sounds reasonable. You want to validate that the technology actually solves a problem before you invest in hardening. So you deploy fast, you cut corners, you get something running, and then once it's proven, you'll retrofit all the governance controls. This assumption is broken for AI in a way it never was for traditional infrastructure. Security debt compounds faster with AI than any other workload type. When you manually deploy a web server without security controls, you can lock it down afterward. You can update the network configuration. You can adjust RBAC. You can add logging. These are overlays on top of existing infrastructure. But with AI, once an LLM has access to sensitive data, removing that access isn't an overlay. It requires redeployment. Think about what happens. You deploy an LLM with a managed identity that has broad access to your SharePoint content. The model works. It grounds reasoning on your proprietary information. The business sees value. Then, months later, compliance reviews the deployment and flags the overly broad permissions. Now, you need to remove that access. The obvious approach: create a new managed identity with restricted permissions. But the LLM is already deployed with the old identity. Changing the identity isn't a configuration update. It means redeploying the entire resource. And if you're redeploying manually, you're repeating all the decisions you made the first time. Did you remember to enable private endpoints this time? Did you configure the diagnostic logging? Did you set up the role assignments correctly? Without Bicep, each redeployment is a new opportunity to miss something. Each time you redeploy, you introduce new vulnerabilities. Enterprise governance requires audit trails. When you deploy manually, there's no trail. You make a decision in the portal, you click a button. Nothing documents why you made that choice or what you intended. When the auditor asks why the LLM has access to that data source, you're guessing at your own reasoning. Manual deployments leave gaps. Not because you're cutting corners intentionally, but because the portal doesn't enforce documentation. It doesn't ask you to justify decisions. It lets you deploy without explanation. The "we'll fix it later" approach becomes impossible at scale. 1 LLM, you can retrofit it. 10 LLMs, you can retrofit them all in a week. 100 LLMs deployed across your organization by different teams using different patterns. Now you're looking at months of work and you're fixing problems you don't even know exist yet. By the time leadership asks for compliance evidence, it's too late to retrofit. You're not missing a few security controls. You're missing the evidence that you ever made a governance decision at all. There's no code, there's no documentation, there's no trail. This is when you realize the liability wasn't the initial deployment. It was the decision to defer security to later. Bicep forces a different model. You secure it from the beginning because the code demands it. What auditors actually look for. The audit begins with a single, deceptively simple question. Show me the code that deployed this resource. In organizations with Bicep, the answer is clear. Here's the module, here's the parameter file, here's the commit history, here's what changed, when it changed, and who approved it. The entire decision trail is embedded in source control. In organizations with manual deployments, the answer is silence. Or worse, a screenshot of the portal from months ago when someone created the resource. That screenshot is now outdated. The configuration has drifted. The screenshot doesn't match what's actually running. And even if it did, a screenshot isn't evidence. It's a picture. It proves nothing about intent or governance. The auditor moves to the next question. Who has access to this LLM endpoint? With Bicep, the answer lives in the RBAC assignments defined in code. The module specifies which roles can read from the endpoint, which can write to it, which can manage it. The code is the source of truth. When someone grants a new team access, that change goes through version control. It's reviewable, it's reversible. Without Bicep, access is scattered. One person added the tenant to the Azure OpenAI resource directly in the portal. Another person created a service principal and assigned it permissions through the CLI. A third person shared an API key through a password manager. Nobody documented any of this. When the auditor asks who has access, the honest answer is, we're not entirely sure. Then comes the question about data flow. How is data moving from your knowledge base to the model? This is where architecture reveals itself. If your knowledge base sits in a private Azure AI search instance, accessible only through a private endpoint with a managed identity handling authentication, then the answer is clean. All data movement is encrypted, on Microsoft's network backbone, never crossing the public internet. It's provable. It's in the code. But if the knowledge base was connected manually, the data path is unknown. Is the search endpoint public? Probably. Is the connection authenticated through a managed identity or through an API key? Unclear. Did someone accidentally enable public network access on the storage account? Possibly. The auditor can't see a clear data flow because it was never designed as a unified system. The conversation shifts to economics. What's your cost attribution model? Which business units are paying for which tokens? Bicep deployments have built-in cost tracking. API management sits in front of the LLM, emitting metrics. Each request carries metadata: tenant, feature, user, cost center. Tokens consumed by the marketing team's co-pilot are tracked separately from tokens consumed by the support team's assistant. You can see where money is going. You can explain it. Manual deployments. Token usage is invisible until the bill arrives. There's no cost attribution. No way to tie spend back to decisions. No way to answer the question, what value did those tokens generate? Finally, the auditor asks the question that matters most. Can you deploy this exact same setup in another region? Can you replicate this infrastructure at the same level of security and governance? The answer from Bicep organizations is yes. The module is portable. It carries all the logic. Deploy it to another region, another subscription, and you get identical architecture, identical governance, identical security. The answer from manual deployments is no. Because the knowledge doesn't live in code, it lives in the heads of the people who built it. And they're no longer sure they remember all the decisions they made. That no is what the auditor was looking for all along. It means you can't scale. It means you can't prove repeatability. It means the structural weakness has been exposed. Bicep as the control plane. Now we move from diagnosis to structure. The question shifts from what went wrong to how do we build it right. Bicep isn't just a tool. When you're deploying AI infrastructure, Bicep becomes the control plane, the declarative system that encodes governance into the deployment itself. Here's the shift in thinking. A tool is something you use to accomplish a task. You pick it up, use it, put it down. Bicep is different. It's a language that doesn't just describe what you're deploying, it describes how governance flows through every resource you create. It's the difference between using a hammer and building a house. The moment you shift to Bicep, something fundamental changes. You're not making individual decisions in the portal anymore. You're writing code that makes the decisions for you, consistently, every single time the module runs. Let me show you what this means in practice. In the portal, you create an Azure OpenAI resource. It's a resource with properties. You set the SQ, you set the region, you click a checkbox for diagnostic logging, then you leave. That's one deployment, one snapshot. The next time someone needs to deploy Azure OpenAI, they start from scratch. They remember some of the decisions you made. They forget others. They might make different choices for reasons they don't write down. In Bicep, you write a module called OpenAI. Bicep. That module doesn't just create the resource. It encodes decisions. Every resource created through that module carries metadata embedded in the code. Ownership, compliance tier, data classification. That metadata flows through automatically. You don't remember to add it. The code adds it, always. The structure of your Bicep modules should mirror the reasoning architecture, not the Azure Service Catalog. This is critical. Most infrastructure code follows the cloud provider's organizational structure, networking modules, compute modules, storage modules. But AI infrastructure isn't organized that way. Your intelligence flows from data ingest through vectorization into retrieval, into reasoning, into output. Your code structure should reflect that flow, not Azure's catalog. When your code mirrors your reasoning architecture, something clicks. You're not deploying a collection of services. You're deploying a reasoning system. The network module isn't about network security in the abstract. It's about keeping your knowledge base private so the reasoning is grounded. The identity module isn't about RBAC in general. It's about ensuring that when the model retrieves context, it only accesses what the current user is authorized to see. The observability module isn't about dashboards. It's about tracking which reasoning decisions consumed which tokens. This alignment matters because it forces you to think architecturally. The moment your code structure matches your reasoning flow, gaps become obvious. If you're deploying a retrieval module but there's no corresponding network isolation, the module itself highlights the gap. The code becomes a structural checklist. Bicep modules become reusable blueprints that enforce security by default. You don't have to remember to add private endpoints. The module includes them. You don't have to remember to enable diagnostic logging. The module enables it. You don't have to remember to create managed identities and assign roles. The module creates them. This is the power of encoding governance into code. The first time you deploy a pattern, it's documented. Every decision lives in the module. There's a reason the private endpoint is created in that specific subnet. There's a reason the managed identity has those particular role assignments. There's a reason the diagnostic setting routes to log analytics. It's all written down. The 100th time you deploy the same module, it's identical to the first time. No drift, no forgotten steps. No, we'll add this later. Every deployment carries the same governance, the same security, the same structure. This consistency is what transforms AI infrastructure from a liability into a controlled system. When you deploy the same pattern 100 times and it's identical every time, you've eliminated the source of most governance failures, human variation. The control plane isn't forcing you to follow rules. It's making the right decisions automatic. It's the difference between an auditor asking, "Why didn't you do this?" and an auditor asking, "How did you ensure this was done every time?" The 3 layers of the hardened perimeter, that consistency, that automatic governance, it comes from structure. The control plane isn't a single decision. It's 3 layers working together, each meaningless without the others. The first layer is the identity perimeter. This is where secrets stop existing in your infrastructure. Not because you've eliminated the problem of authentication, but because you've eliminated the human from the problem. When you deploy without Bicep, you create a managed identity or you generate an API key. Then you store that key somewhere, in a configuration file, in a key vault, in an environment variable, and immediately you've created a secret that can leak. Not because you were careless, but because secrets have a gravitational pull toward exposure. They get copied, they get shared, they get stored in places they shouldn't be. Bicep flips this. You don't create secrets, you create identities. The module defines a managed identity on your compute resource. It assigns that identity specific roles. It grants that identity access to specific services. No keys change hands. No human ever sees the secret. Azure manages it cryptographically. This isn't optional governance. This is structural. The moment you deploy through a Bicep module that creates managed identities as the default, keys become the exception, not the rule. And exceptions get noticed. They trigger policy violations. They show up in audits. The RBAC layer sits on top. Role assignments are defined in the same code that creates the identity. The identity exists. Its permissions are defined alongside its creation. When you update one, you update the other. They don't drift apart. They can't get out of sync. The second layer is the network perimeter. This is about where your data actually moves. Not theoretically, but physically. Through which networks, over which connections, with what exposure. Private endpoints are the mechanism. They create a private IP address inside your VNet that maps to an Azure service, Azure OpenAI, AI search, storage, key vault. Traffic destined for that service no longer routes across the public internet. It stays on Microsoft's network backbone. It never leaves your security boundary. But private endpoints are only useful if they're consistently deployed. If one team creates them and another doesn't, you have an architecture where some data movement is protected and some isn't. The network perimeter is broken. Bicep makes this decision once. The module for deploying Azure OpenAI doesn't just create the service, it creates the private endpoint in the correct subnet. It links the private DNS zone. It enforces NSG rules that restrict traffic. It validates that public access is disabled on the target service. This layering is critical. The private endpoint is useless without DNS. The DNS is useless without the NSG rules. And all of it is useless if someone can still access the service through its public endpoint. Bicep ensures that all these pieces deploy together. It's structural. The perimeter exists because the code makes it impossible to deploy without it. The third layer is the reasoning perimeter. This is where AI actually happens. This is where Azure AI Foundry sits as the governance boundary that defines which models are available, which data sources can be accessed, which tools can be invoked. Alongside it, API management becomes the gateway that controls every request flowing to the LLM. And observability becomes the visibility layer that tracks every token flowing through. These 3 components, Foundry, API management, observability, they're only powerful together. Foundry without API management means you can't enforce rate limits or attribution. API management without Foundry means you're controlling traffic to a governance-free system. Observability without either means you can see tokens flowing, but you can't control them. Bicep wires them together as a unit. When you deploy the reasoning perimeter through a single module set, they're automatically connected. The API management backend points to the Foundry project. The diagnostics from both flow into the observability layer. They're not 3 separate decisions. They're one integrated architecture. Each layer is meaningless without the others. That's the design. Identity without network means secrets can still move across the internet. Network without reasoning means you've secured the infrastructure, but not the intelligence. Reasoning without observability means governance is happening in the dark. Bicep ensures all 3 are deployed together, consistently, across every environment. Manual deployments inevitably skip layers. Someone forgets the private endpoint. Someone skips setting up API management. Someone deploys observability but doesn't wire the metrics correctly. The perimeter only works if it's complete. Modular Bicep for AI search and vectorization. Let's look at the first concrete pattern, how Bicep structures the vector data path. Azure AI Search isn't just a search service. That's the old way of thinking about it. You deploy search as a tool. You index documents. You query them. It's a database with better search capabilities. In the AI context, search becomes something fundamentally different. It's the grounding mechanism. It's how you prevent hallucinations. When an LLM generates text, you want it grounded in facts from your knowledge base, not from patterns in its training data. Search is what makes that possible. It retrieves relevant context. The LLM uses that context to reason. Without it, you're asking the model to make things up. This reframing changes how you deploy it through Bicep. In the portal, someone creates an Azure AI search service. They index documents, they're done, it works in isolation. But when you structure it through Bicep for AI reasoning, the service exists as part of a reasoning pipeline. The module doesn't just create the search service, it creates the service, the private endpoints, the managed identities, the vector configuration, and the integration with the embedding model. All of it deployed as a single unit. Here's what that module must handle. First, the search service itself. It needs to exist with public access disabled, not disabled later as a follow-up task, disabled from the moment it deploys. The Bicep module creates the service with that configuration baked in. Anyone using the module gets a search service that's locked down by default. Second, private endpoints for client access. The module creates the endpoint in the correct subnet. It links private DNS zones so clients can resolve the search service name to the private IP. Without this, any application trying to query the search service would either need to configure complex DNS or route across the public internet. The module eliminates that complexity. Third, managed identities for indexer access to data sources. This is critical. When search indexes documents from SharePoint or a SQL database, it needs to authenticate. The old way is to store credentials. The Bicep way is to create a managed identity, assign it permissions on the data source, and let the indexer use that identity. No credentials stored, no secrets to leak. Fourth, vector profiles and embedding model configuration. This is where the reasoning happens. The module specifies which embedding model should generate vectors for documents. It defines the vector profile, the algorithm that will be used for similarity search, the dimensions of the vectors, the distance metric. This configuration ties search directly to your embedding service. They're not separate, they're a single unit. Fifth, integrated vectorization. This is the pipeline that chunks documents, generates embeddings, and indexes them automatically. The module wires this up so that documents flowing into search are chunked according to your strategy, embedded using your embedding model, and indexed into vector fields. It's one pipeline, not three separate operations. The module structure separates concerns, but they all deploy together. The network concern, private endpoints and DNS, is isolated in code. The identity concern, managed identities and role assignments, is clear. The search configuration is distinct. The vectorization pipeline is explicit. But when you deploy the module, they're wired together. They're a system. This modularity creates flexibility that manual deployments never have. 6 months in, you realize your chunking strategy isn't optimal. Documents are being split at sentence boundaries, but your use case needs paragraph boundaries. In a manual deployment, fixing this means going back to the indexer definition, changing the chunking configuration, and redeploying everything connected to search. With Bicep, you update the module. You change one parameter that controls chunking strategy. You redeploy. The indexer is updated. Documents are re-indexed with the new strategy. Everything else stays the same. No risk of accidentally breaking something else because you weren't manually configuring every piece. Without this structure, you're changing infrastructure in the dark. With Bicep, you're updating a known, tested, reusable pattern. This is how you scale reasoning. Not by deploying search once, but by having a module you can deploy 50 times in 50 different contexts, knowing every deployment is identical, compliant, and grounded in the right vector strategy. Private endpoints as code. The network perimeter is where most deployments fail. Here's how Bicep fixes it. Private endpoints aren't optional for enterprise AI. They're not an add-on. They're not something you implement if you have time. They're the foundational mechanism that keeps LLM traffic off the public internet, and without them, you're accepting data exposure as a cost of doing business. Here's what most organizations don't understand. When you connect an LLM to your knowledge base, that connection is happening somewhere. Either it's happening across a private network backbone that Azure controls, or it's happening across the public internet. There's no middle ground. The question isn't whether the traffic has an attack surface. The question is how large that surface is. Manual private endpoint creation invites inconsistency. One team creates a private endpoint for Azure OpenAI, configures the DNS correctly, and sets up the NSG rules. Another team creates a private endpoint for AI search, but forgets to disable public access on the search service itself. Now the endpoint exists, but it's useless because traffic can still flow to the public endpoint. A third team creates a private endpoint for storage, links it to the wrong DNS zone so name resolution fails. Applications can't connect even though the infrastructure is technically in place. Bicep modules solve this by encoding the complete pattern in code. The module doesn't just create the endpoint, it creates the endpoint in the correct subnet. It links the private DNS zone for name resolution. It enforces NSG rules that restrict traffic to that endpoint. It validates that the target service has public access disabled. All of this happens in a single deployment. All of it is documented. All of it can be audited. The critical insight is reusability. A single Bicep module for private endpoints can be reused for Azure OpenAI, AI Search, Storage, Key Vault, SQL databases, and any other Azure service that supports private link. You're not writing 5 different modules. You're writing one module that's parameterized for different services. This matters because consistency becomes automatic. When you deploy Azure OpenAI through the same private endpoint module you used for storage, they follow identical security patterns. The endpoint is created in the same subnet. The DNS zone linking is identical. The NSG rules follow the same logic. You're not hoping that all your private endpoints are secure. You know they are because they all came from the same template. The module handles specifics that vary by service. The group IDs differ between Azure OpenAI and AI Search, for example, but the structural pattern is identical. The module abstracts away the service-specific details and enforces the universal principles. Private network first, name resolution configured, traffic restricted, public access disabled. Manual private endpoint creation leaves gaps, not intentionally, but because the process requires multiple steps and humans miss steps, you create the endpoint. Did you link the DNS zone? Probably. Did you link it to the right zone? Maybe. Did you verify that the target service has public access disabled? Possibly, but it's easy to forget. Did you document why you chose that specific subnet for the endpoint? No. The next person deploying a similar endpoint has to guess at your decisions. Bicep modules eliminate the gaps because the module is the documentation. When someone wants to know why a private endpoint was created in that specific subnet, the answer is in the code. When they want to understand the naming convention for the DNS zone link, it's in the module. When they need to replicate the pattern, the module is the blueprint. No gaps, no guessing, no forgotten steps. This is how you scale the network perimeter, not by hoping that every team configures private endpoints correctly, but by making the configuration automatic, reusable, and identical across every deployment. The network perimeter isn't something you check after the fact. It's something that can't be deployed incorrectly because the code enforces correctness. Managed identities and the identity perimeter. The identity layer is where governance either succeeds or collapses. This is where the structural decision you make in Bicep determines whether your AI infrastructure is auditable or opaque. Managed identities are the only way to eliminate secrets from your infrastructure. Not reduce them, not hide them better. Eliminate them. Because once a secret exists in a configuration file, an environment variable, or a connection string, it exists. Someone will find it. Someone will copy it. Someone will put it somewhere it shouldn't be. The lifecycle of a secret once created is inevitably toward exposure. Think about what happens without Bicep in this layer. A developer needs to authenticate an application to Azure OpenAI. The easy path is to create an API key, copy it, paste it into a just net configuration file, or into an environment variable on the VM, or into a parameter on the function app. The key is now in multiple places. Multiple people have access to it. It's in version control history, probably. It's been shared in Slack, maybe. The likelihood that it stays secret approaches 0. Managed identities invert this dynamic. They are cryptographic identities that Azure manages for you. You don't create them, you don't see them. You don't copy them anywhere. The infrastructure declares that a service needs to authenticate as itself, and Azure handles the mechanics. No human ever touches the credential. Bicep is where this declaration happens, and it's where the identity perimeter becomes structural or becomes a wish. The module must define system-assigned identities on compute resources. When you deploy a VM that hosts your reasoning orchestration layer, or a function app that coordinates LLM calls, or an AKS cluster running AI agents, that resource needs a system-assigned identity. This identity belongs to the resource. It can't be shared. It can't be compromised through key exposure because there's no key. Azure issues a cryptographic token when the resource needs to authenticate. The resource uses the token. The token expires. A new one is issued. No human interaction. The module must also define user-assigned identities for shared services. Some services need to act on behalf of multiple resources. An indexer might need to read from multiple data sources. An agent might need to access different services for different types of queries. A user-assigned identity can be attached to multiple resources, letting them all authenticate as that identity without each needing its own key. But here's where most manual deployments break. RBAC assignments. You can create the identity, but if you don't assign it the right roles, it's useless. It has no permissions. When the application tries to authenticate and access a resource, it fails. In manual deployments, this is a separate step. You create the identity, then you remember maybe to assign it roles. Maybe you assign the right roles. Maybe you assign too many roles to make the application work, violating least privilege. Bicep handles this as a unit. The module creates the identity and assigns the roles in the same declaration. They're not separate decisions. They're part of the same infrastructure definition. The identity exists with exactly the permissions it needs. Not more, not less. The module must also handle key vault access policies. Some services legitimately need secrets, database passwords, encryption keys, API credentials for external systems. These secrets live in key vault. But the service can't just read any secret. It can only read the secrets it's authorized to read through a specific access policy tied to its managed identity. Again, Bicep makes this structural. When you deploy a service through the module, it's granted access to the specific secrets it needs from Key Vault, not access to the vault in general, not access to all secrets, access to these specific secrets. The policy is defined in code, auditable, and reviewable. The identity perimeter fails if any component uses a key instead of an identity. A single API key embedded in configuration breaks the entire model. Bicep enforces this by making identities the default and keys the exception. The module structure makes identities automatic. Creating a key requires a deliberate override, which stands out in code review. This is structural governance, not a policy you hope teams follow, a code pattern that makes the right choice the path of least resistance. Azure policy as the reasoning framework. Bicep deploys the infrastructure, but deployment is only half the equation. Once it's deployed, it needs to stay compliant. And that's where Azure policy enters. Azure policy is the control plane for everything that comes after infrastructure exists. It's the enforcement layer that says, these are the rules. Every resource deployed in this subscription must conform to these rules. If it doesn't, we block it. Think of what happens without policy. You deploy your Bicep modules. The identity perimeter is correct. The network perimeter is locked down. But then someone else in the organization working independently deploys an AI service directly in the portal. They skip the private endpoint. They enable public access to save time. They justify it as temporary. 3 months later, that temporary deployment is still running, still public-facing, still violating your governance baseline. Azure policy prevents this by treating governance as a technical enforcement, not a policy document. Policy definitions are rules written as code. They can restrict which models are deployed from the Azure AI Foundry catalog. They can enforce private endpoints on all AI services, making it technically impossible to deploy an Azure OpenAI service without one. They can require specific regions for data residency if you're in a jurisdiction that mandates where data physically lives. They can mandate encryption at rest and in transit, ensuring that every deployment meets security baselines automatically. The key insight is this. Policy should be written in code, not enforced manually. When policy lives only in documents, governance frameworks printed on shared drives, compliance checklists scattered across wikis, it's aspirational. It describes what should happen. Azure policy makes it happen automatically. Bicep and Azure policy are designed to work as a pair. Bicep deploys the infrastructure according to the architecture you've defined. Azure policy enforces that the infrastructure conforms to governance rules you've written. The moment someone tries to deploy something that violates policy, Azure doesn't deploy it. There's no debate, there's no exception process. The deployment fails. Azure policy returns an error explaining which rule was violated and why the resource can't be created. This is governance by design, not governance by exception. Most organizations run governance by exception. You have a rule. Someone breaks it. You grant an exception. The exception becomes permanent. 3 exceptions become a new baseline. Before long, nobody remembers what the original rule was. Governance by design inverts this. The rule is enforcement. Exceptions require explicit override, which creates an audit trail. If someone needs to deploy a resource outside policy, they can't do it silently. They have to declare the exception, document why it's needed, and explain when it expires. The override is visible. It's trackable. When you combine Bicep modules with Azure policy, something powerful happens. Teams deploy using the modules because that's the fastest path. The modules create resources that conform to policy by default. Even if someone tries to deploy a non-compliant resource directly, policy blocks it. You've created a system where compliance is easier than non-compliance. For AI specifically, this changes governance dramatically. Policy can restrict which models teams are permitted to deploy from the Foundry catalog. This isn't about preventing innovation, it's about preventing chaos. If your organization has decided that only models that have passed internal red teaming are approved for production, policy enforces that. When a team tries to deploy an unapproved model, they can't. They don't discover this limitation after deployment. They discover it during development when they can still pivot to an approved alternative. Policy can mandate that all AI services have private endpoints, not as a recommendation, as a requirement. The moment someone tries to deploy Azure OpenAI with public access, policy blocks it. There's no negotiation, there's no temporary exemption that becomes permanent. The only way to deploy is the secure way. This is where the control plane concept becomes real. Bicep describes the infrastructure. Policy describes the rules that infrastructure must follow. Together, they create a system where correct deployment is automated and incorrect deployment is prevented, not just detected. When a deployment violates policy, Azure blocks it automatically. The failure message tells you why. You update your infrastructure to conform and deployment succeeds. This creates a feedback loop where teams learn the governance rules through interaction, not through reading documentation. This is how you scale governance in an enterprise, not by hoping teams follow rules, but by making the rules technical requirements that the platform enforces. Management groups and the organizational model. Bicep deploys resources. Management groups organize them. Together, they create accountability. Here's the distinction that most organizations miss. Azure subscriptions are the billing boundary. They're where cost gets tracked and charged to a department or business unit. But subscriptions aren't where governance lives. Governance lives in management groups, the hierarchy that sits above subscriptions and determines which rules apply to which workloads. This hierarchy is critical because it's how you organize your entire cloud estate as a coherent system, not as isolated silos. Management groups are the organizational structure for policies. When you assign a policy to a management group, every subscription under that management group inherits that policy. When you assign a policy at a subscription level, only that subscription gets it. The hierarchy determines scope. For AI workloads specifically, the structure typically separates concerns by workload class. This separation isn't arbitrary. It reflects different security, compliance, and operational requirements. The first category is Corp. This is internal AI, systems that employees use to improve their productivity or that the organization uses internally to automate processes. A co-pilot for sales teams. An agent that summarizes internal documentation. A system that analyzes your own data. These systems touch proprietary information, but they're not exposed to external users. The security baseline is high. Data classification is strict, but the approval process can be faster than systems exposed to the public. The second category is online. These are customer-facing AI systems, public chatbots, external APIs, systems that third parties can interact with. Security is still critical, but the threat model is different. You're protecting against external attackers, not just internal data leakage. The data flowing through these systems is typically less sensitive. Information you've already decided to publish publicly or information your customers provide to the system explicitly. The third category is confidential. These are regulated workloads, AI systems that handle financial data, healthcare information, personal data, subject to GDPR or any other data classification that demands encryption in use, advanced audit trails, and intense compliance scrutiny. These deployments move slower. They require additional approval steps. They demand stronger evidence of governance, but they're organized in their own management group so that the policies governing them don't inadvertently restrict innovation in the corp and online categories. Each management group inherits policies from its parent. This inheritance is structural. When you create a policy at the root level, all AI resources must have diagnostic logging enabled. That policy applies to corp, online, and confidential. They all inherit it. This creates a universal baseline. No AI workload, regardless of classification, can be deployed without logging. But policies can also be assigned at intermediate levels. A policy saying data residency must be within the EU applies only to subscriptions in a Europe-specific management group, not to subscriptions in North America. The hierarchy creates fine-grained control while maintaining baseline consistency. This inheritance is critical because it means security baselines are applied automatically to every new subscription. When a new team creates a subscription under the Corp management group, the policies governing the Corp hierarchy are automatically active. That team doesn't have to know about the policies. They don't have to manually assign them. The policies are there because of the structure. Bicep modules should be designed to work within a specific management group context. This doesn't mean the modules are aware of the management group directly. It means the modules are designed with the assumption that certain policies are already in place. A Bicep module for deploying an AI workload in the Corp hierarchy can assume that policies enforcing private endpoints are active. The module doesn't need to include workarounds for public access. It builds infrastructure, assuming the policy-enforced baseline exists. When you deploy a Bicep module, it inherits the policies of its management group automatically. The module creates the resource. The policy evaluates whether the resource conforms. If it does, deployment succeeds. If it doesn't, deployment fails. This removes the need for manual policy assignment because the policy is inherited through the hierarchy. This creates a scaling dynamic that manual systems can't achieve. You're not assigning policies to individual resources or individual subscriptions. You're defining a management group hierarchy that reflects your organizational structure, assigning policies at appropriate levels, and then letting that structure govern deployments automatically. The result is accountability that flows from structure, not from hope. Bicep and Azure AI Foundry integration. Now we connect Bicep to the actual AI platform, Azure AI Foundry. If everything we've discussed so far, the identity perimeter, the network perimeter, the policy enforcement, is the foundation, then Azure AI Foundry is the orchestration layer where AI governance actually happens. This is where models get selected, where data sources get connected, where agents get deployed, where reasoning happens. Foundry is the unified control plane for AI model deployment, evaluation, and governance. It's not another service. It's the workspace where intelligence gets assembled. And the moment you understand that, you understand why Bicep becomes essential here. In the portal, someone creates a Foundry hub manually. They select a region, they pick a SKU, they create a project underneath it, they connect Azure OpenAI to the project, they link Azure AI Search for retrieval, they attach a data source. Each connection is a separate decision point. Each one is a place where something can go wrong or get forgotten. With Bicep, the hub and all its connections deploy as a unified system. The module creates the hub with managed identities already configured. It creates projects with data classification and compliance tags embedded. It connects to search with the correct identity and network settings. It integrates OpenAI with the right endpoint and access controls. It attaches log analytics so that every reasoning decision gets logged. These aren't 5 separate deployments. They're one coherent architecture expressed in code. The hub becomes the governance boundary. This is the critical distinction. The hub defines what's available to teams working within it. Which models can they access? Only the ones you've added to the hub's model catalog. Which data sources are available? Only the ones you've connected. Which tools can agents invoke? Only the ones you've registered. The hub isn't just a container. It's a governance enforcement point. Without Foundry as a unified boundary, governance fragments. One team connects a data source directly to an agent. Another team uses the hub's connection. A third team uses neither and imports data into their agent through a different mechanism. Now you have 3 different data governance models within the same organization. When an auditor asks how data flows to your LLMs, the answer is inconsistent. With Foundry as the boundary, data flows through a single orchestration layer. Teams don't bypass it, they can't. The hub is the only way to access approved models and data sources. Governance becomes enforced by architecture, not by hope. But here's where Bicep matters most. The hub is only a boundary if it's deployed consistently. If one team creates a hub with strong RBAC controls and another creates a hub without them, you have 2 different governance models within the same organization. Bicep ensures that every hub, every project, every connection follows the same pattern. The Bicep module for Foundry deployment must handle a specific set of concerns. Hub creation with managed identities and RBAC. The identity perimeter extends into Foundry. Project creation with data classification and compliance tagging. The governance tags that flow through your entire infrastructure are embedded at the project level. Connection to Azure AI Search for grounding. The knowledge base is linked through managed identity, ensuring that only authenticated access happens. Integration with Azure OpenAI for inference. The reasoning engine is wired with the correct endpoint and throttling. Attachment to log analytics for observability. Every agent decision, every model call, every token consumption flows into unified logging. These aren't optional capabilities you add later. They're the default structure. The module creates nothing without them. No hub exists without RBAC. No project exists without tagging. No data source connects without proper identity. Without Bicep, these connections are manual and inconsistent. You get partial governance. You get gaps. You get the assumption that everyone will implement best practices and the disappointment when they don't. With Bicep, the connections are automated, repeatable, and auditable. The module is the governance enforcement. Deploy it twice, and you get identical architecture both times. No variation, no gaps, no prayer that this deployment is more secure than the last one. The reasoning perimeter, where Foundry sits, where orchestration happens, where governance becomes real, only works if it's structured, and structure comes from code, not from hope. Policy-driven model governance. Here's where the reasoning layer enforces control. Model selection. The infrastructure is in place. The identity perimeter secures access. The network perimeter isolates traffic. The Foundry hub orchestrates connectivity. But none of that matters if you can't control which models actually get deployed. A developer could choose an unapproved vendor, could select a model that hasn't been validated, could deploy reasoning engines that your organization has deliberately decided not to use. Without enforcement, infrastructure governance is meaningless because the intelligence running on top of it is uncontrolled. Azure Policy solves this by restricting which models can be deployed from the Foundry catalog. This matters because enterprises face real constraints that models must satisfy. Vendor risk is one of them. If your organization has decided that only Microsoft-hosted models are acceptable in production because you've negotiated specific data handling terms, or because you've completed due diligence on Microsoft but not on OpenAI or Anthropic, then a policy can encode that decision. When a developer tries to deploy a non-Microsoft model, the policy blocks it. No negotiation, no exception process. The deployment fails and the developer learns the boundary immediately. Licensing is another constraint. Some organizations license certain models for specific use cases, and the licensing terms don't permit unlimited deployment. Policy can enforce licensing boundaries. A model might be approved for internal use, but not for customer-facing applications. Policy can encode that distinction, blocking the model from deployment in production subscriptions while allowing it in development. Compliance is the third constraint. Your organization might have decided that only models that have passed internal red teaming, adversarial testing to detect safety flaws, are deployable to production. Or only models that meet specific accuracy standards, or only models that have been evaluated for bias or fairness. Policy turns those decisions into technical requirements. When the evaluation team completes testing on a new model and approves it, the policy gets updated. the model becomes deployable. When testing is incomplete, the policy blocks deployment. The specific rules look simple in code but powerful in practice. A policy that says only Microsoft-hosted models are allowed in production means every production Foundry hub inherits that constraint. A developer working in a production project opens the model catalog. They see only Microsoft models. Non-Microsoft options aren't visible. This isn't hidden complexity, it's visibility working in your favor. The developer knows what's available. They don't waste time requesting a model you've already decided not to use. A policy that says only models that have passed red teaming are deployable ties model governance to your evaluation process. Before a model can be used, it must be tagged as red teamed in your Foundry model registry. The policy checks for that tag. If the tag is missing, deployment fails. This creates accountability on both sides. Evaluation teams know their work feeds directly into availability. Development teams know that available models have been validated. A policy that says only models in approved regions can be used ensures compliance with data residency requirements. If your organization operates in Europe and data residency laws demand that LLM inference happen within Europe, a policy can enforce this. Non-European models become unavailable. The policy doesn't require developers to understand the regulation. It bakes the regulation into the platform. When a developer tries to deploy a model that violates policy, Azure blocks it automatically. The error message explains which policy was violated. The developer updates their deployment. Everything else stays the same. This is governance without friction. Developers stay productive. Teams move fast, but they move within guardrails that the organization has deliberately chosen. Bicep doesn't write these policies, but it deploys the infrastructure that Azure Policy governs. Together, they create a system where compliance isn't something you hope happens, it's something the platform enforces. Token-level observability as governance. Deployment and governance are only half the picture. The other half is visibility. You can build the hardened perimeter, you can enforce policy, you can lock down identity and network. But if you can't see what's happening inside your reasoning system, governance is theoretical. You're controlling infrastructure, you're not controlling intelligence. Token consumption is the fundamental unit of AI economics. Every prompt contains input tokens, every response contains output tokens. Cost flows directly from token usage. You can't separate them. 1,000 token calls to GPT 3.5 costs less than 100 token calls to GPT 4. The difference is exponential. This isn't an implementation detail. This is business economics. Observability isn't about dashboards, it's about governance. You can't control what you can't measure, and you can't measure what you don't instrument. The moment you decide observability matters, you're deciding that token-level visibility is non-negotiable. It's foundational. Token-level observability means tracking specific things. Input tokens per prompt component, system messages, user input, retrieved context from your knowledge base all count separately. Output tokens per response, cost per token for each model you're using because different models have different pricing tiers. Cost attribution by feature, team, or business unit so you know which parts of your organization are driving which costs. This isn't metadata. This is the data that determines whether your AI strategy is economically sustainable. Without token-level visibility, several things become impossible. You can't detect runaway costs before the bill arrives. You think you're spending $5,000 a month on AI. The bill shows $50,000. The spike wasn't gradual. It was invisible until the invoice arrived. You can't optimize prompts and retrieval strategies because you don't know which prompts are consuming the most tokens. A prompt that seems like it's working efficiently might be retrieving 10 times more context than necessary, wasting tokens and money. You can't justify AI spending to finance teams because you have no evidence of value relative to cost. You can't prove compliance to auditors because you have no way to show which data flowed through which models or how many times it was processed. This is why observability becomes governance. The moment you instrument token consumption, you gain control over it. You can set budgets. You can alert when spending spikes. You can attribute cost back to decisions. You can make informed choices about model selection based on actual usage patterns, not guesses. Bicep must deploy the monitoring infrastructure that makes this visibility possible. This isn't optional, it's structural. The moment you create a Bicep module for deploying an AI workload, that module includes observability by default. It deploys application insights to capture telemetry. It configures diagnostic settings to route logs from all AI services into log analytics. It wires up alert rules that trigger when token consumption exceeds thresholds. It creates the data structures needed to aggregate tokens by feature, team, and business unit. The module doesn't ask whether observability is wanted. It doesn't provide an option to skip it to save money on monitoring costs. Observability is the default. Removing it requires deliberate override, which creates an audit trail. Why would a team disable monitoring? The question itself becomes suspicious. Here's what this means in practice. When you deploy Azure OpenAI through a Bicep module, the deployment doesn't just create the service. It creates the service, configures diagnostic logging, sets up alert rules for token thresholds, creates the namespace and application insights where token metrics will flow, and wires everything to log analytics. All of this happens in a single deployment. There's no separate step to enable monitoring later. There's no forgetting because all the components deploy together. Without this structural integration, observability becomes fragmented. You have token metrics in one place, cost data in another, and no connection between them. You can see tokens consumed, but not which feature consumed them. You can see costs on the bill, but not which decisions drove the costs. You have visibility into components, but not into the system as a whole. With Bicep enforcing observability by default, token-level visibility becomes automatic. Governance gains teeth. You're not hoping teams report their usage. You're measuring it. You're not asking whether costs are being tracked. You're aggregating them. You're not wondering whether you can answer auditor questions about token flow. You have the data because the data collection was built into the foundation. Bicep and FinOps integration. Observability connects to cost governance through FinOps patterns. This is where measurement becomes accountability. FinOps is the discipline of managing cloud costs through visibility and accountability. It's not about spending less, it's about spending intentionally. You make conscious decisions about where your money goes, based on data, not on hope. You allocate budget to the features that matter most. You eliminate waste in the features that don't. You hold teams accountable for the costs they incur. For this to work, you need three things: visibility into spending, attribution of spending to decisions, and automation that makes governance repeatable. For AI workloads, FinOps translates into token tracking, cost attribution, and budget enforcement. Tokens are the currency. Each token costs money. The cost varies by model, by region, by whether you're using input or output tokens. FinOps for AI means converting that token consumption into business accountability. You track tokens. You attribute them to features or teams. You set budgets based on expected token usage. You enforce those budgets through automation, not through manual reviews that happen months after the damage is done. Microsoft provides a FinOps toolkit that includes Bicep modules for cost ingestion and reporting. This isn't theoretical. This is a concrete set of deployable components that turns FinOps from a concept into infrastructure. The toolkit includes modules that pull cost data from Azure Cost Management, normalize it according to the Focus standard, a vendor-neutral cost data schema, and feed it into Power BI for reporting. This normalization matters because it means your cost data looks the same whether you're analyzing Azure OpenAI or storage or compute. It's one unified language for talking about spending across your entire cloud estate. The Bicep modules deploy cost management exports that run on a schedule, pulling detailed cost and usage data from your Azure subscriptions. They deploy log analytics workspaces that aggregate token metrics we discussed earlier. They deploy Power BI dashboards that visualize cost trends in real time. They deploy alerts and budgets that trigger when spending exceeds thresholds. All of this happens through code. All of it can be versioned, reviewed, and replicated across environments. Here's the critical difference between FinOps with Bicep and FinOps without it. Without Bicep, you set up cost governance once. Someone deploys the cost ingestion infrastructure in one subscription. Someone else configures the Power BI dashboard. A third person sets up the alerts. They're ad hoc decisions made by different people at different times. If you need the same cost governance in another subscription, you have to repeat all those steps manually. Or you don't, and that subscription has no cost visibility. You end up with some subscriptions that have cost tracking and some that don't. Your finance team has partial visibility into the landscape. They can see costs in some areas but not others. With Bicep, you build the cost governance once and replicate it. The Bicep modules that deploy cost ingestion, log analytics, dashboards, and alerts become your organizational standard. Every subscription that hosts AI workloads gets the same cost governance. Not because you manually deployed it to each one, but because you deployed the Bicep module to each one. The output is identical every time. You don't have to remember which Power BI workspace to connect to which log analytics instance. The module handles it. You don't have to manually configure alert thresholds. The module includes them. Bicep makes FinOps repeatable in a way that manual infrastructure never can. Without it, cost governance is fragmented and inconsistent. You have visibility into some areas of spending, blindness in others. You enforce budget controls in some projects but not others. Some teams can see their token consumption. Others have no idea how much they're spending until the invoice arrives. This is how organizations discover 6 months later that a single AI feature has burned through hundreds of thousands of dollars that nobody was tracking. With Bicep, cost visibility is automatic and standardized. Every AI deployment includes cost governance because every AI module pulls the cost governance infrastructure in with it. You don't have to remember to enable monitoring. You don't have to manually wire up alerts. The tokens are measured, the costs are attributed, the budgets are enforced, all because the infrastructure was built that way from the start. Azure Monitor and Application Insights for AI. Token metrics flow into Azure Monitor, where they become actionable intelligence. But the infrastructure that captures those metrics is more complex than simply turning on logging. Azure Monitor is the observability platform for every Azure resource. It's the system that sits behind the scenes collecting signals about what's happening across your infrastructure. For traditional workloads, VMs, databases, storage accounts, the signals are straightforward. CPU utilization, memory consumption, disk I/O, network throughput. Straightforward because the metrics map directly to operational health. AI workloads are different. The operational metrics matter, latency, error rates, availability, but they're not the full story. You need to know what's actually happening inside the reasoning pipeline. Token usage per request tells you consumption, but you also need latency broken down by component. How long did retrieval take? How long did the model think? How long did post-processing consume? Error rates matter, but you need to distinguish between transient errors, a temporary network issue that the system will retry, and systematic failures that indicate architectural problems. Model performance and quality metrics matter most. Is the model actually answering questions correctly? Are retrieved documents actually relevant? Is the safety filtering too aggressive, rejecting legitimate requests? Application insights is where these signal layers come together. It's the application-level observability layer that understands your code and your business logic, not just the infrastructure underneath. When your code makes a call to Azure OpenAI, Application Insights captures that moment. It records custom properties, which feature triggered this call, which user made the request, which tenant owns the user. It captures prompt and completion metadata, the length of the prompt, the model used, the temperature, and max token settings. It records evaluation scores that your code calculated. Did a secondary model judge this response as hallucinated? Did a safety check flag it? Did a grounding validator confirm that the response was supported by retrieved context? This layering matters because no single tool tells the complete story. Azure Monitor shows you metrics. Application Insights shows you traces. Together, they create a unified view of what's happening in your AI system. You're not jumping between tools to answer questions. You're querying a unified observability platform. Bicep handles the wiring. The module must deploy diagnostic settings that route logs from all AI services, Azure OpenAI, AI search, storage, log analytics itself, into a central log analytics workspace. The module must deploy Application Insights instances with the correct instrumentation keys so that when your applications run, they automatically emit telemetry to the right place. The module must deploy alert rules that trigger when cost spikes exceed expected thresholds, when latency anomalies occur, or when error rates climb above acceptable levels. The integration is critical. When you deploy an AI workload through Bicep, the observability infrastructure deploys with it. Azure OpenAI sends its diagnostic logs to log analytics. Application Insights captures trace data from your orchestration layer. Both flow into the same workspace. You can query across both. You can create alerts that fire when metrics from different layers cross thresholds simultaneously. High token usage combined with high latency, for example, suggesting a retrieval problem. Without this unified deployment, observability fragments. Your token metrics live in one tool. Your latency data lives in another. Cost attribution happens in a third place. You're not observing your system. You're observing its shadows fragmented across multiple platforms that don't talk to each other. With Bicep enforcing unified observability as a default, visibility becomes coherent. The moment you deploy, you can see what's happening. You understand token flow, you understand cost, you understand where latency is accumulating, you understand whether your safety controls are working, you understand whether your retrieval is actually grounding the model or just adding noise. This visibility doesn't happen because you remembered to configure it. It happens because the infrastructure was designed that way from the start. Cost attribution and chargeback. Once you can measure token usage, you can attribute cost to who caused it. This is where observability transforms from a technical capability into a business accountability mechanism. Cost attribution is critical for enterprise accountability, and without it, AI spend becomes a black box on the cloud bill. Finance reviews the charges. They see a $150,000 monthly spike for cognitive services. They have no idea which feature drove it. They can't tell whether the cost came from legitimate production workloads or from experimentation that should have stopped months ago. They can't justify the spend to their leadership. They can't forecast whether AI spending will become a runaway line item in the budget. When you have cost attribution, everything changes. You know which business units are consuming the AI infrastructure. You can see that the sales department's Copilot is costing $40,000 monthly. The customer service department's bot is running $30,000, and internal productivity tools are burning through another $50,000. You see which features are consuming the most tokens. You discover that one specific feature, maybe an experimental agent that didn't work out, is consuming 40% of your token budget despite driving almost no business value. You identify which teams are deploying inefficient prompts. One team is using a 50-page system prompt when a 5-page system prompt works just as well. Another team is retrieving 20 documents from your knowledge base when the top 3 contain 95% of the relevant information. These aren't architectural problems, they're implementation problems, but you can't see them if cost is invisible. With attribution, you can see them, call them out, and fix them. Bicep enables cost attribution by encoding the infrastructure that makes attribution possible. The first requirement is consistent tagging. Every resource created through Bicep carries tags: cost center, business unit, environment, owner. These tags aren't suggestions, they're enforced by the module. If you want to deploy an AI resource through Bicep, that resource gets tagged. The tags flow into cost management. Finance can filter spending by tag. They can group by cost center and see what each department spent. They can filter by environment and see how much is flowing to production versus development. The second requirement is tracking at the gateway level. API management sits between clients and your LLM endpoints. Bicep deploys APM with the infrastructure to track usage per client or per subscription. Every request flowing through APIM is logged with context about who made the request. That context is stored in log analytics. Later, you can query that context and map requests back to cost. Feature X made 10,000 requests last month. Feature X consumed an average of 250 tokens per request. That's 2.5 million tokens of cost. You can attribute that cost back to the team that owns Feature X. The third requirement is wiring token metrics into log analytics with cost attribution dimensions. When you log a token consumption event, you don't just log the count, you log it with context. Who triggered this? Which feature, which tenant, which business unit? That context becomes a dimension in your reporting. You create pivot tables. You slice cost by feature, by team, by business unit, by any dimension that matters for accountability. The final requirement is Power BI reporting that breaks down spend by tag. Finance shouldn't have to write KQL queries in log analytics. They should open a Power BI dashboard and see, here's monthly spending by business unit. Here's which features consume the most tokens. Here's the trend. Is AI spending growing or shrinking? That dashboard is built by someone once. The Bicep module deploys the data infrastructure. Power BI connects to log analytics. The dashboard queries the data automatically. Every month, new cost data flows in and the dashboard updates. The key insight is this. Cost attribution is only possible if your infrastructure is designed for it from day one. You can't retrofit attribution onto a system that wasn't designed for it. Manual deployments don't have this design. Resources get deployed without tags because tagging is optional. API calls happen without logging because logging wasn't built in. Token consumption gets recorded without context about who triggered it. By the time you realize you need attribution, the infrastructure doesn't support it. Bicep deployments can be architected with cost attribution as a first-class concern. The module includes tagging, it includes IPM wiring, it includes log analytics dimensionality, it includes the data structures that Power BI needs. You don't add attribution as an afterthought, you deploy it. API management as the AI gateway. The perimeter is in place. Now we need a gateway that controls traffic through it. Everything we've built so far creates a boundary. Identity perimeter, network perimeter, reasoning perimeter. But a boundary only works if traffic actually flows through it. The moment you have an AI endpoint, you have a critical decision. Will clients connect directly to that endpoint, or will they connect through a gateway that controls their access? Direct connection is the easy path. Developers get the endpoint URL. They get the API key. They call it directly from their application. For a proof of concept or an internal experiment, this works. For an enterprise, it breaks immediately. Because the moment clients connect directly to your LLM endpoints, governance disappears. API management is the gateway that changes this. It sits between clients and Azure OpenAI, and everything that flows between them passes through APIM first. This matters because APM enforces layers of control that exist nowhere else. Authentication and authorization is the first layer. Clients don't authenticate directly to Azure OpenAI. They authenticate to APIM. APM validates the credential. If the client is authorized to make this request, APM forwards it. If not, APM rejects it. This seems like a small difference, but it's structural. Azure OpenAI has no visibility into who's really making the request. APIM does. APIM knows the client identity, it knows the tenant, it knows the subscription. It can make sophisticated authorization decisions based on that context. Rate limiting and quotas is the second layer. Without APIM, a single misbehaving client can consume your entire token budget in an afternoon. With APM, you set rate limits per client. Maybe the sales team's copilot gets 1 million tokens per day. The customer service bot gets 500,000. Experimentation tools get 100,000. When any of those clients hits their limit, APIM throttles them. They get a 4 or 29 response. They have to back off. Your infrastructure doesn't get drowned by a single runaway workload. Request and response validation is the third layer. APIM can inspect requests before they reach Azure OpenAI and responses before they reach clients. You can validate that requests conform to your standards. Maybe you've decided that the maximum prompt length is 100,000 tokens. APIM can check the incoming request, count tokens, and reject the request if it exceeds that limit. On the response side, you can validate that responses conform to your safety requirements. If a response triggers a safety concern, APIM can block it before it reaches the client. Cost tracking and billing is the fourth layer. When a request flows through APIM, you can extract metadata about that request and log it. Who made the request? Which feature triggered it? How many tokens did it consume? APIM can emit that data to application insights. Later, you can reconstruct the entire cost history of your AI infrastructure by tenant, by feature, by client. You have the granularity that manual deployments never achieve. Bicep must deploy APIM with all of this wired together. The module doesn't just create the API management instance, it creates the instance with policies embedded that emit token metrics to application insights. It configures backends that point to private Azure OpenAI endpoints, not the public endpoints. The traffic never touches the public internet. It defines products and subscriptions that map to business units or teams. Each product has its own rate limit policy. The module includes the rate limit policies themselves, not as configuration you add later, but as part of the infrastructure definition. When you deploy a PIM through Bicep, you get a functioning gateway immediately. Clients have endpoints to call. Those endpoints route through APM. APM enforces authentication, rate limits, validation, and logging. The moment you start using the gateway, you start accumulating visibility into who's doing what. Without APIM, clients connect directly to Azure OpenAI, bypassing all governance. With APIM, every request is visible, controlled, and attributed. APM becomes the single point of governance for all LLM traffic. This is where the hardened perimeter closes. The identity, network, and reasoning layers create structure. APM is where that structure enforces behavior. It's the enforcement point that makes governance real instead of theoretical. Orchestration and reasoning chains. The gateway controls traffic. Now we need to control how that traffic flows through reasoning. Enterprise AI workloads aren't single model calls. A user makes a request. The system doesn't just send that request to Azure OpenAI and return the response. What actually happens is far more complex. The system retrieves relevant context from your knowledge base. It structures that context for the model. It calls the model with the context and the user's question. The model responds. The system validates that response, checking whether it's grounded in the retrieved context, checking whether it violates safety policies, checking whether it makes sense. If validation fails, the system might call the model again with different parameters. If it passes, the system stores the result, logs the interaction, and returns the response to the user. That's one complete reasoning chain, a single interaction that flows through multiple steps, multiple services, multiple decision points. Most enterprises have dozens of these chains running simultaneously. Some are simple, retrieve and answer. Some are complex, retrieve, analyze, retrieve again, call external APIs, aggregate results, validate, respond. The complexity grows as your organization scales AI usage. Azure AI Foundry agents are the orchestration layer where these chains get defined and controlled. An agent isn't just a model, it's a system that coordinates reasoning. You can define multiple agents with different roles. A retrieval agent focuses on finding relevant information in your knowledge base. An analysis agent takes that information and performs calculations or transformations on it. An action agent takes the analysis results and makes changes in other systems, creating records, sending notifications, triggering workflows. Bicep must deploy these agents as a coherent system. The module doesn't just create an agent, it creates the agent with specific roles defined. It registers the tools that agents can invoke, connections to your APIs, your databases, your external services. It sets up evaluation flows that test agent behavior before it reaches production. It configures monitoring that tracks how agents are performing once they're live. This is where governance becomes architectural rather than aspirational. Most governance failures in AI orchestration happen because agents have too much autonomy. An agent is created, it's given access to a data source and some external API. Nobody explicitly controls what the agent can do with those tools. The agent tries something unexpected. Data flows somewhere it shouldn't. An API gets called with parameters that break something. The organization discovers the failure when it's already caused damage. Bicep prevents this by enforcing governance at the orchestration layer. When you define an agent through Bicep, you restrict which data sources the agent can access. You don't give the agent access to your entire knowledge base. You give it access to specific indexes, specific document sets. If the agent needs to read customer data, you define that permission explicitly. If the agent shouldn't be able to modify data, only read it, you enforce read-only access. The permissions aren't something the agent requests and gets because nobody set up controls. The permissions are defined in code before the agent is created. Role-based permissions for agent actions follow the same pattern. An agent might be able to invoke certain APIs, but not others. The analysis agent can call your internal calculations API, but not your payment API. The action agent can update records in one database, but not another. These permissions are enforced by Bicep configuration, not by hope that the agent developer will implement them correctly. High-risk operations require human approval. If an agent is about to delete a record or transfer money or send a message to thousands of customers, the Bicep configuration can require explicit human approval before the operation proceeds. The agent doesn't just do it. The orchestration layer pauses. It alerts a human reviewer. The human confirms the action. Only then does the agent proceed. Every agent decision gets logged for audit purposes. Not just the final result, but the reasoning chain itself. Which data sources did the agent query? Which tools did it invoke? What parameters did it pass? What was the response? Each step flows into your observability layer. An auditor can reconstruct the entire chain of reasoning that led to a decision. The orchestration layer is where reasoning actually happens. It's also the place where governance enforcement becomes possible. Bicep structures that enforcement so governance isn't added later. It's built in from the start. Data governance and RAG patterns. Agents need knowledge to reason. That knowledge must be governed. Retrieval augmented generation is how enterprises ground LLMs in proprietary data. The pattern is straightforward conceptually. Before the model generates a response, the system retrieves relevant documents from your knowledge base and passes them to the model along with the user's question. The model reads the retrieved context and answers based on it. This solves a critical problem. It prevents the model from hallucinating answers and keeps responses tied to sources your organization actually owns. But RAG introduces a new governance challenge that orchestration patterns don't fully address. When you retrieve documents to pass into an LLM, you're not just selecting information. You're exposing that information to the model's reasoning process. If those documents contain sensitive data, customer information, financial records, proprietary research, you're now allowing the model to process that data. The question becomes, who should the model be allowed to see? If user A asks a question and user B's confidential data appears in the retrieved context, has the model just leaked information? This is where data governance becomes architectural rather than aspirational. When documents enter your knowledge base, they must be classified by sensitivity level. Public data can appear in retrieved context for any user. Internal data should only appear for employees of your organization. Confidential data should only appear for people with explicit clearance. Restricted data shouldn't appear in LLM contexts at all. It's too sensitive to risk exposure, even to a model, but classification alone doesn't solve the problem. You also need filtering based on user permissions. A document might be classified as internal, but that doesn't mean every employee should see it. Maybe it's internal finance data. Only finance team members should get that document in their retrieved context. Maybe it's HR records. Only HR and authorized managers should access it. The retrieval system needs to know who's asking the question, check their permissions, and only include documents they're authorized to see. This filtering happens at query time, not at index time. The same document might appear in retrieved context for one user and be filtered out for another asking nearly identical questions. Audit trails must track what got retrieved and used. When an LLM generates a response based on retrieved context, you need to know which documents were included. If something goes wrong later, a user claims they received incorrect information, or an auditor questions how a decision was made, you can reconstruct the exact context the model was working with. Bicep structures this entire pattern. The module deploys Azure AI Search with private endpoints and managed identities. Traffic doesn't leak onto the public internet. The search service only accepts connections from authorized services using cryptographic identity, not API keys. The module creates data source connections to SharePoint where your documents live, to SQL where structured data sits, to Cosmos where your knowledge graph might be stored. These connections use least privilege access. The indexer that reads from SharePoint doesn't have permissions to write. It doesn't have access to anything except the specific document library you've designated as the knowledge base. The indexing pipelines respect data classification. As documents get indexed, metadata about sensitivity gets attached. A skill in the indexing pipeline reads document properties, determines the classification level, and tags each indexed document. Later, when the model queries, the search service can filter based on those tags and the current user's permissions. Query time filtering enforces user permissions. When a user makes a request, the orchestration layer captures their identity. That identity flows with the search query. The search service filters results to include only documents the user has permissions to access. The model receives only documents that have passed both the classification check and the user permission check. Without governance baked into the infrastructure, RAG systems leak. Documents get indexed without classification. Permissions don't get checked. The same query returns different results for different users or returns results that shouldn't be visible to any user. An auditor asks which documents were used in a specific response and discovers that audit logging was never enabled. Bicep deployments eliminate these gaps. The infrastructure enforces classification, permissions, and audit trails from day one. Bicep modules is organizational DNA. We've covered the architecture. Now let's talk about how organizations actually scale this. The moment you build your first Bicep module, you've created something that looks like infrastructure code. But what you've actually built is institutional memory. A well-designed module encodes years of lessons learned. It captures decisions about how identity should work, how data should flow, how governance should enforce itself. When a team deploys that module, they inherit all of that knowledge automatically. They don't have to rediscover what works. They don't have to make the same mistakes you already made and learned from. This is what we mean by DNA, not the biological metaphor, but the structural sense. DNA is how an organism passes its patterns forward. It's how complexity reproduces consistently. A Bicep module is the same thing for your infrastructure. It's how the organization passes its patterns forward. Deploy it once and the pattern is documented. Deploy it 100 times and it's identical every time. No variation, no drift. The organizational knowledge doesn't live in a Slack conversation or a wiki page that gets outdated. It lives in code that gets executed. Enterprise organizations typically build a library of modules arranged by function. There's a core AI infrastructure module that deploys the perimeter we've spent the last few sections discussing. It creates the hub, sets up the network isolation, configures the identity layer, attaches observability. One module, one deployment, everything we've talked about gets instantiated. Teams don't build this themselves. They deploy the module. On the first day they use it, they have the hardened perimeter. On the 100th deployment, they have it again. No learning curve required beyond understanding how to invoke the module. But one core module isn't enough for scale. Organizations build specialized modules for specific patterns. There's a RAG module that deploys AI search with all the data governance patterns we discussed. There's an agent orchestration module that sets up agents with role-based permissions and audit logging. There's a fine-tuning module that handles the infrastructure for custom model training. Each module specializes. Each one handles a specific type of workload, but they all follow the same patterns established in the core module. They all include identity perimeter, network perimeter, observability. They just specialize the reasoning layer for their specific purpose. Governance modules live in this library too. There's a module that deploys Azure policy assignments for AI workloads. It defines which models are allowed, which regions are permitted, which tagging standards are enforced. The module takes parameters, your organization's specific policies, and wires them in. Different business units might have different policies. The module accommodates that through parameterization, not through manual policy assignment. Observability modules complete the picture. There's a module that deploys the entire monitoring stack. Log analytics workspace, application insights, alert rules, Power BI dashboards, all pre-configured and wired together. Teams don't design their own observability. They deploy the module. They immediately have visibility into tokens, cost, latency, errors. The module does the wiring. Humans do the analysis. Here's the scaling dynamic. Teams don't write their own infrastructure. They consume modules. This ensures consistency across the organization. You don't have one team implementing identity one way and another team implementing it differently. Every deployment of the core module creates the same identity structure. This reduces the surface area for mistakes. A team can't accidentally skip the observability layer because the module includes it. They can't deploy without private endpoints because the module enforces them. Over time, the module library becomes the organization's institutional knowledge. New teams onboard faster because the patterns are already proven. A team wants to build an AI feature. They find the RAG module. They deploy it. They inherit years of learning about how to structure vector search, how to handle data governance, how to track retrieval quality. They don't have to invent this. It's already encoded in the module. The library also creates a feedback loop. When a team discovers a better way to handle something, the module gets updated. Every subsequent deployment includes that improvement. The organizational learning propagates forward instead of getting siloed. A security team discovers a better way to configure managed identities. The core module gets updated. The next 100 teams that deploy automatically benefit from that discovery. This is how enterprises scale from one AI pilot to hundreds of production workloads without creating chaos. Not by hoping teams will follow best practices, not by writing documentation that becomes obsolete, but by encoding the practices into modules and making the modules the default way infrastructure gets built. CI/CD and infrastructure validation. Modules are deployed through pipelines, not manually. And that distinction is structural. The moment you have a Bicep module, you have something that can be validated before it reaches production. This is where infrastructure as code stops being just a convenience and becomes a governance mechanism. Manual infrastructure gets deployed first and discovered to be broken later. Bicep infrastructure gets validated before it ever touches your environment. The validation happens in CI/CD pipelines. When a developer pushes a Bicep module to source control, the pipeline wakes up. It doesn't immediately deploy. It runs a series of checks. Each check is automated. Each one prevents a category of mistakes from reaching production. The first check is linting. Bicep has a linter that checks code for syntax errors, missing parameters, unused variables, formatting inconsistencies. It catches the obvious mistakes: typos in resource names, incorrect property types, logic errors. A module that fails linting doesn't move forward. The developer gets immediate feedback. They fix the issue locally. They push again. The pipeline runs again. This catches problems at the speed of development, not at the speed of discovery after deployment. The second check validates that the module complies with Azure policy. This is critical and non-obvious. You can have syntactically correct Bicep that violates your organization's policies. Maybe the module tries to deploy an AI service in an unapproved region. Maybe it creates resources without the required tagging. Maybe it doesn't include private endpoints where your policy mandates them. The validation check queries your Azure policy definitions and tests the module against them. Will this module, when deployed, violate any policies? The pipeline determines that before you ever hit Azure. If it would violate policy, the deployment fails. The developer is forced to fix the module to comply with policy before it can proceed. The third check tests that the module actually deploys without errors. This uses a what-if deployment. The pipeline spins up a temporary environment, runs the Bicep module against it, and checks whether all resources get created successfully. The what-if deployment doesn't actually create the resources. It simulates the deployment and reports what would happen. If any part of the deployment would fail, the pipeline catches it. Maybe the module tries to reference a resource that doesn't exist. Maybe it tries to create a child resource on a parent that doesn't support children. The what-if deployment finds these issues before they become production incidents. The fourth check verifies that deployed resources have the correct configuration. After the what-if deployment runs, the pipeline queries the simulated environment and checks that resources have the expected properties. The RBAC assignment is configured correctly? Yes. The private endpoint is linked to the right subnet? Yes. The managed identity has been created? Yes. Any mismatch between what the module intended and what actually got created triggers a failure. Again, the developer fixes the module. They push again, the pipeline validates again. The fifth check runs security scans to detect misconfigurations. There are tools that look at your infrastructure and ask, could this be hacked? Are there ways that an attacker could exploit this? Does this resource expose secrets? Is there a path to privilege escalation? These tools scan the what-if deployment results and report security issues. If critical issues are found, the pipeline fails, the developer remediates. The pipeline tries again. Only after all of these validations pass should the module be deployed to actual Azure. Not because humans are afraid to trust other humans, but because validation is faster than remediation. Catching a mistake during CI is a 30-second fix. Catching a mistake after it's deployed to production is a 3-hour incident. Preventing the mistake entirely is better than both. This automation prevents specific categories of failure. Configuration drift happens when resources change over time in ways the code doesn't reflect. A human logs into Azure and manually updates something. The Bicep module still exists, but it no longer represents reality. With CI/CD validation enforcing that modules deploy consistently, drift becomes obvious. You update the module, the pipeline validates, you deploy. The infrastructure stays aligned with code. Policy violations get prevented. Without pipeline validation, developers could deploy resources that violate organizational policy. With validation, they can't. Policy gets enforced before deployment, not after. Security misconfigurations get caught. Resources exposed to the internet when they shouldn't be. Encryption not enabled. Weak authentication. The security scans find these and block deployment. Audit failures become impossible. Every deployment goes through the same validated pipeline. Every module gets linted, policy checked, tested, and scanned. Every deployment creates an audit trail. You can show an auditor exactly what validation happened and that it passed. CI/CD for infrastructure is non-negotiable for enterprise AI. It's the difference between hoping deployments are correct and knowing they are. From liability to asset, your AI landing zone is a liability if it's built manually. Governance, observability, and security end up as afterthoughts, not part of the foundation. Bicep transforms it into an asset. Automated, auditable, scalable. The hardened perimeter isn't a single control, it's the integration of 5 structural layers deployed together. Identity through managed identities and RBAC. Network through private endpoints and VNets. Governance through Azure policy and management groups. Observability through token tracking and cost attribution. Orchestration through AI Foundry and API management. When these layers deploy together through Bicep, they create a system where compliance is automatic, cost is visible, data is protected, and reasoning is auditable. This is how enterprises scale AI without chaos. The alternative is shadow AI, audit failures, and uncontrolled costs. Your choice is clear. Build the perimeter with Bicep or inherit the liability.